Let's discuss interpolation. We are given a sequence xn. We would like to derive a continuous time function x of t. That process is done through interpolation. So given a sequence, surely the simple thing to do is to put a staircase function. So we start with x at the origin, x0, and we simply continue, x1, continue, x2, we continue, and so on, and that would be the staircase function from these samples. That's called piecewise constant interpolation, and the formula would be x of t is equal to xn for n smaller or equal to t smaller to n plus 1. Module 6.2 Interpolation. The overview is that we're going to look first at polynomial interpolation. You're given a bunch of points and you would like to fit a curve that goes through the points, and that's a well-known problem of interpolation. Then we'll look at local interpolators, which are short functions that do also an interpolation job. And last but not least, we will look at sinc interpolation. This sinc, which is a function we have seen now several times in this class, is a very important interpolator because it will generate an output that will be strictly band-limited. Therefore, the output will live on a subspace, the subspace of band-limited functions. This subspace, we will see, is critical for sampling results. The interpolation question is very elementary. You have a sequence xn, you want to generate x of t, and you would like to fill the gaps between the samples. How should we best do this? So here is an example. We have 5 blue samples indicated by the sticks. They are equally spaced in time, and we fit the red curve smoothly through the samples. Note that it is exact at the sample values, and this is smooth in between. So the requirements are, we have to decide on TS, the spacing between the samples in the continuous time function. We have to make sure that x at the location n times ts is equal to the sample values xn. And we would like, in general, that xt is a smooth function. We'll see more precisely what we mean by a smooth function. Let us discuss the issue of smoothness in physical terms. Assume x of t shows the location of an object. If there is a jump, it would mean there is infinite speed. If there is a second-order discontinuity, it means there would be infinite acceleration. In general, we would like interpolators to be infinitely differentiable, so they make also physical sense. A natural solution for this is polynomial interpolation. So how to do polynomial interpolation? Well, if you have n points, there is a polynomial of degree n-1 that can go through these n points. For example, give me 2 points, I can draw a straight line. Give me 3 points, I can draw a parabola, etc. So we have p of t, which is an n-1 degree polynomial, and we simply fit the polynomial to the sample. So p of 0 has to be equal to x0, p of ts, x1, etc. up to p of n-1 times ts. Introduce an interval symmetric around the origin, so call it in from minus capital N to n, set ts equal to 1. We can always rescale the axis to achieve any ts. And then we want to fit p of minus n to the sample x of minus n, etc., p of 0 to the sample x0, up to pn to the sample xn. The natural solution to this interpolation problem is given by Lagrange interpolation. Take Pn, the space of degree 2n polynomials over the interval In. A basis for Pn is a family of 2n plus 1 Lagrange polynomials given by this formula. Let us just do a small example, namely n is equal to 1. So let's write the formula again. Ln of t is this product with k going from minus n to capital N. Pick capital N is equal to 1, so we have 3 polynomials, L minus 1, L0, and L1. Let us calculate L0 of 1. So L0 of 1 of t is this product where k cannot be equal to 0 of t minus k over minus k. This is equal to t plus 1 times t minus 1 divided by minus 1, so that's 1 minus t squared. We can plot this, and sure enough, it's a parabola, and it is equal to 1 at the origin, and equal to 0 at minus 1, and also 0 at plus 1. For completeness, you can calculate L1 of 1, it's t squared plus t over 2, and L minus 1 of 1, which is equal to t squared minus t over 2. Let's plot the next bigger example. This is capital N is equal to 2, so we have 5 Lagrange interpolators. The first one is L minus 2, 2 of t. It is 1 at minus 2, 0 at minus 1, 0, 1, and 2. The second one in blue is L minus 1. It's equal to 1 at minus 1, 0 at the other integers. L0 of 2, which is symmetric around the origin, where it's equal to 1. L1 of 2, which is the black curve. And finally, L2 of 2, which is the light blue curve. The important thing is that these polynomials are 1 at their index n, and they are 0 at the other integers. Each one has exactly this characteristic. So now we have a formula. P of t can be written as a linear combination n going from minus n to n of xn, the samples, and the respective Lagrange interpolator of index n. Let us summarize what has been achieved. The Lagrange interpolation is what we were looking for. It's a unique solution to the interpolation problem. It satisfies Pn is equal to xn because of the interpolation property of the Lagrange polynomial. Let us return to our problem of interpolating 5 samples between minus 2 and plus 2. We can now do this by writing the solution as a linear combination of Lagrange interpolators weighted by the sample values. Let's do this now. First Lagrange interpolator centered at minus 2, then at minus 1, at the origin, at 1, at plus 2, summed together, we find the red curves that we had seen before. The key property of polynomial interpolation is that it's maximally smooth. You can take infinitely many derivatives. The drawback is that the interpolation bricks, each piece we add depends on n, and each piece actually looks different, for example, in the Lagrange interpolation case. Let's look at some other interpolation possibilities. So as always, we have to decide on the spacing between the samples at capital Ts. We need to make sure that at that location, nts, the x of t is equal to the samples xn, and we would like x of t to have a certain smoothness. Maybe not infinitely differentiable, as we had seen with polynomials, but at least some smoothness. The first example is piecewise constant interpolation. So take the sample at the origin, for example, and put the continuous time function at that value between minus a half and plus a half, etc. around all the samples. So it's a staircase function that has the correct value at the samples and its neighborhood, but of course it is not continuous, it has discontinuous points. What are the characteristics of this zeroth order interpolation? So x of t is given by this formula. You take the index t plus 1/2 and the floor function that indicates which sample you use for the piecewise constant interpolation. So x of t is simply written as a linear combination of xn rect of t minus n. So the interpolation kernel is this rect function, sometimes called the zero-order hold. The interpolator has a short support of length 1, however the interpolation is not even continuous. We start with the same 5 samples as usual. We put the first box function around minus 2, then minus 1, at the origin, at 1, at 2, and the sum is this piecewise constant function with discontinuous points at half integers. The next simplest interpolation is first order or piecewise linear. You simply draw a straight line between the samples. This is the so-called connect the dots strategy. X of t is now the linear combination of an interpolation kernel I1 shifted to the location of the samples and weighted by the samples xn. This interpolation kernel is also called the hat function or the triangle function because it's simply 1 minus the absolute value of t on the interval minus 1 to 1. The support now is of length 2, so it's longer than the previous interpolation kernel, and the interpolation is now continuous even though the derivative is not. We can see this interpolation on our usual 5-sample discrete sequence. So we have a hat function at minus 2, at minus 1, at 0, at 1, at plus 2. The sum is this red function, which is piecewise linear and continuous by construction. So we have seen I0 and I1, so probably there is higher order interpolator like this. One that is interesting is third order interpolation. So x of t is a linear combination of I3 in these shifted versions. The interpolation kernel is put together from 2 cubic polynomials. The support is of length 4, and this one is continuous up to second derivative. So we can do our usual construction with our 5 samples. The cubic interpolator at minus 2, minus 1, 0, 1, 2, and the sum, which is this very nice smooth red function. So we have seen now several local interpolation schemes. They all work the same way. You have a kernel, IC, it is moved to the location of the sample, weighted by the sample, and that's how you interpolate x of t. The requirement is that the interpolation kernel at 0 is equal to 1, and it's equal to 0 at t being a non-zero integer. So it's the interpolation property we had seen for Lagrange. We have seen it, of course, for the box function or the square. We have seen it for the hat function or the triangle, and it was also the case for the cubic interpolation just before. Let's look at these 3 interpolation kernels again. So first, the box or rectangle function. Second, the triangle function. Third, the cubic interpolator. You can see they become larger and smoother. The key properties of these local interpolators are the following. It's the same interpolation function independently of n and independently of location. This was not the case of Lagrange interpolation. Another advantage is the short support of the interpolation kernel. The drawback is the lack of smoothness. There is a remarkable result that links the sinc interpolation scheme with the Lagrange interpolation scheme. Namely, if you take a Lagrange interpolator of order capital N, and you take the nth indexed one, as n goes to infinity, then this tends to think of t minus n. So in the limit, local and global actually are the same interpolation schemes. So we have a sinc interpolation formula as a limit of Lagrange interpolation, namely that x of t is equal to the sum of xn, think of t minus nts divided by ts. This is a very elegant and very powerful formula. Let us look at sinc interpolation at work. So we'll have a sinc kernel centered on every sample. So the first one at the origin, then at plus 1, plus 2, 3, 4, 5, etc. You see the sum of them now as a red curve, very smooth, very nice. So we have now the interpolated version through the samples, and this is the sinc interpolation of a discrete time sequence. The proof that the Lagrange interpolator goes to the sinc function as n goes to infinity is rather technical. It is given in the book, so please look it up if you're interested. The intuition is that both think of t minus n and ln at infinity of t share the same set of infinite number of zeros, which is given here in the last 2 formulas of the slide. We can explore this equivalence between the sinc function and the Lagrange interpolator numerically. So let's start with the sinc function here in green, centered at the origin, then a Lagrange interpolator of order 100, and you can see it's a good fit around the origin, not so good towards the end of the interval. L200, it's a better fit, still not perfect. L300, even better. And you can see where it is going, and we know, or we can prove that in the limit, these two functions will be the same.